Last chapter, chapter 8, we introduced concepts for chemical bonding. And in chapter 9, the authors couldn't think of anything else to call it, I guess, so they called it chemical bonding orbitals. And we've been talking about orbitals from the beginning. But in this chapter, we're going to discuss hybridization, which is a part of the localized electron model, the valence bond theory. And here we go. All right. So the hybridization is a kind of a fix to the valence bond theory. And that's all we're going to cover today. This is going to be part 1. Next Monday, I've left the discussion of molecular orbitals till then. That'll be part 2. So we don't have to rush. We've got another class period to get through it. So here we share the PowerPoints. And let's see, where am I? I gotta move stuff out of the way so I can get to my controls here. Slideshow, come on. From the beginning, there we go. So let me move this up out of the way. All right. So chapter 9. Before we get started with chapter 9, I should open the floor for any questions or comments. If not, or if you think of something, interrupt me. Or if you'd rather talk to me privately, I'll be back at let's see, 3:45 with connection through CHEM101, the lab tutorial. Okay, so here's the problem that the localized electron model encountered. We're going to use methane as an example. It happens several places with different compounds. Methane is a covalent compound, and if we draw the Lewis structure, we have 4 electrons for that carbon, and then 4 electrons for the hydrogens because there are 4 of them. So we have 8 electrons. Now the Lewis structure will put carbon in the middle, and then each of these hydrogens around here like that. Okay, so that's everything. 2, 4, 6, 8. All the electrons are used. That's all you can do with them. Okay, what does the VSEPR model say about the shape of this molecule? If it's got 4 groups around the central atom, it should be tetrahedral, correct? Tetrahedron. So it would be something like that, with a carbon in the middle and hydrogens all around like that. Okay. And the bond angles, of course, we would expect to be 109.5 degrees. That's typical for a tetrahedral molecule. Okay, here's the problem. The valence bond theory says that you get bonds when orbitals, atomic orbitals, overlap. So let's look at it this way. What orbitals are going to overlap? Well, you're going to have carbon overlapping with 4 hydrogens. So it's got to have one for each of the hydrogens because they're single bonds. Okay, so let's look. The hydrogen electronic configuration is going to be 1s1. That's it. It has an s orbital. No big deal. Carbon has 6 electrons. So it's going to be 1s2, 2s2, 2p2. Okay? Now, what do we know about the s orbitals? They're all spherical, right? So you've got carbon with this spherical orbital around here. So this is your s orbital. How about the p orbitals? The p orbitals are kind of lobe shaped. So they would be like, actually there are 3 of them. That one goes back into the board and comes out of the board like that. Okay, so if you're going to overlap atomic orbitals, this s there's room for well, actually this one doesn't count because it's not a valence. We're only counting these, right? So you have this s here and those s's, and you can overlap 2. Well, actually, you can't overlap s because it's full. What am I thinking? You can overlap 2 here with the p orbitals here. The s orbital's full. It can't overlap. So you can only get 2 bonds out of that carbon. Well, the molecule is not this. Molecule is that. So how do you get 4 bonds out of that? All right, that was the problem with the valence bond theory. So the solution, right, there's the electronic configuration for carbon. And you can't get everything you want bonded. You can only form 2 bonds with the theory as it stood. So an experimental evidence says that's the molecule. We know that one. Plus, all the bonds are equal in length and equal in bond angles. So that tetrahedral shape is true for methane. So the solution was to tweak the theory. Remember, you got 3 choices with a theory. When it falls on its face, you can either throw it away and start over. You can restrict its use. You can't use it in certain areas. You can only use it in certain places. Or you can tweak it. You can modify it. And that's what happens here. So we modified it with a concept called hybridization. Okay. Hybridization takes existing atomic orbitals that are in the same valence shell. In other words, these could be hybridized because they have the same principal quantum number, right? You don't hybridize these with that one. You only hybridize the ones with the same n equals number. So you got how many here? Well, how many p's do you have? Right, you have 3 p's, correct? 3 p orbitals. You have 1 s. So if you mix those together and come out with an equivalent, you have that 1 s and you have the 3 p's put together. And that gives you 4. You have 4 of these equivalent orbitals, which are constructed from the s and the 3 p's. But they're still atomic orbitals. They have to be, based on the theory, valence bond theory, localized electron model. these orbitals have to belong to that atom, to that carbon. And then you can overlap them with others and make bonds. Okay, well, a little historical reference. This solution, this fix, was first proposed and developed by Linus Pauling, 1931, for these simple molecules. And it solved the problems, right? For a while, it solved many of the problems that they were experiencing with trying to explain real molecules in terms of their theory. So when do these, when does this process happen? Well, if it's a free carbon atom, it's going to be like this. It's going to have an S, 2 electrons in the S and 2 in the P's. But when it encounters an atom with which conditions are favorable to react, in this case hydrogen, then it's going to automatically mix in order to accommodate the hydrogens that it wants. So it's only in the presence of the hydrogens that the hybridization occurs. And this required actually significant modifications to the equations that are used to do these orbital calculations in quantum mechanics. Right? So the equations that they use to produce this electronic configuration with the quantum numbers had to be modified so that they would yield this in those special situations. Okay, those are just points of information. And obviously we're not going to be crunching any of those equations. Okay, so Sp3 hybridization is the combination of that 1s and the 3p orbitals that are available in the second principal quantum number. So whenever you have 4 equivalent bonds, or if you have 4 equivalent bonds and lone pairs, then you are looking at an Sp3 hybridization because it produces those 4 equivalent orbitals. They're identical in in shape, and they're positioned in such a way that they minimize repulsions. So here's what you get with the hybridization. When you mix the S and the P's together, you get an energy, you get these equivalent orbitals, but there's somewhere in between energy levels of P's and S's. That's what this is trying to illustrate. In the free carbon atom, you have the S down here and the P's up there. That's expected. But if you're going to have equivalent orbitals, and the word in chemistry for that is degenerate. When you hear that word in reference to chemistry, don't think it's some kind of name for a pervert. Degenerate orbitals are those that are equivalent energy. So these 4 orbitals are equivalent in energy, and they're derived from the P's and the S's. And they have a different look to them, right? I mean, the formulas, the quantum mechanical formulas and the calculations yield a different appearance for the orbitals. Here you have the spherical S, and here you have the dumbbell-shaped p orbitals. But when you put them all together, you get 4 equivalent shapes pointing in toward the apex the apices of a tetrahedron. Okay, so that's what it would look like with a space filling model of electron density in the orbitals for hydrogen and carbon in this methane molecule. How about the ammonia molecule? Well, let's see, what are we expecting? With ammonia, right, you have 3 electrons there. Nitrogen has 5. So you have 8 electrons again. Only this time you have nitrogen with a lone pair up there, and you have hydrogen here, and hydrogen in the back. So you have this triangular base. And the electronic structure, according to the VSEPR model, is tetrahedral. But of course, the molecular structure is trigonal pyramid. Okay, we got that out of the way. Now what do we have? Well, we just did that. We wrote the structure. We did the Lewis structure, and then we deduced the molecular structure. Now, what kind of hybridization is required for this bonding to take place? So there's our molecule. We got 4 pairs, so it's tetrahedral. That means tetrahedral always means Sp3 hybridization. Always means tetrahedral. And that's tetrahedral electronic structure. Okay, so one of those Sp3 hybrid orbitals is going to have a lone pair in it. Okay, so there's your lone pair, and the other 3 orbitals actually form bonds with the hydrogens. And this Sp3 orbital with the lone pair in it is going to balloon some because it's not confined by bonding between 2 atoms. It can kind of spread out. That's why these orbitals here, they're going to be less than 109.5 degrees. How about ethylene? What's the shape of an ethylene molecule? C2H4. Okay. So we know this exists. That's a real compound. So we've got to explain it. All right, so we've got 2 times 4 is 8 plus 4 is 12 electrons. Okay. Then we put these 2 carbons together, and then we put the other hydrogens around it. So it's 2, 4, 6, 8, 10. So we have 2 electrons left. Where are they going to go? Well, it doesn't matter. Put them on either one like that. But now we have to make the octet, correct? So we take that lone pair and we make a double bond out of it. Okay, so there's your Lewis structure. No lone pairs. All the electrons are used in bonding. And remember, when we talk about electronic and molecular structures, we're talking about a central atom. So this atom can have one structure and this atom can have another structure. Of course, in this case, they're equivalent. You can see that just by looking at the molecule. So if we do one, we've actually done the other one. So we look at that one and say, how many groups? There's 3 groups around it. So with 3 groups, we've got trigonal planar, correct? Trigonal planar. Okay. How many orbitals, equivalent orbitals, do we need for a trigonal planar with a 120-degree orbital? So around that one, we've got this triangle. That's our trigonal planar right there. And the bond angle is 120 degrees, right? Each one of those angles is 120 degrees. So how do we get that? Well, we need 3 equivalent orbitals, correct? So how do you get 3 out of hybridization? Well, you start with S, and how many more P's do you need? You only need 2, correct? So you only need to hybridize 2 p orbitals. Okay? That gives you the trigonal planar. But that only accounts for single bond overlap. Single bond, single bond, single bond. You got a double bond in there. So there's another bond that has to form from somewhere. Well, you've got 1 p orbital here. Let's say X and Y are used for that hybrid. You've got a PZ that's not used yet. So you got this p orbital here, and you got a same over here and here. And remember that lone pair at first, before we formed the bond, was sitting up here. That goes into these p orbitals. And those p orbitals overlap and give you the double bond. So the only hybrid orbitals are S and 2 p's. And then the third, unused p, is how you form that extra bond. All right? So there's your shape. And there's the expected bond angle. Like that. So we don't need sp3 because that would give us 4 equivalent orbitals, and we don't have 4 groups, right? We have to abide by the ground rules for the localized electron model. Right? Sp3 would give us tetrahedral geometry, and we can't, you know, it just won't work. So sp2 hybridization has to work. Okay, we've got a special name for this bond. This double bond, that extra bond there that was formed, that's called a pi bond. Or like this, right? The Greek capital letter pi. It's the same one used in this area of a circle, pi r squared. But here it means an extra bond. The single bond that forms here, and the first one there is called a sigma bond. Sigma bonds always form on axis between atoms. So what does that mean? That means you can only have one of them. Right? There's not room for more than one sigma bond. But since pi bonds form off axis, then you can have 2 of those, right? You can have, and you have 2 lobes, right? Top and bottom, this way, and then you can have 2 this way, right? So if you have 2 pi bonds, now you've got a triple bond, okay? But you can't form a pi until you've got a sigma. Okay. Oh, okay. Forgot I had a slide.
I lost my connection. I'm sorry.
Oh, no problem. No problem. Yeah. I'll just keep rambling on like I usually do.
I'll keep listening.
Okay, so this is just in black and white and blue, what I just said. Sigma bonds are electron pairs that are shared on axis between 2 atoms. The pi bonds, each pi has 2 electrons, off axis bonding. Now that may sound funny, right? Because the way we draw it here, how are those 2 bonds going to overlap? I mean, they're sticking like that. They're going to have to squeeze over like that. Well, this is a representation of the p orbital that allows us to see other things that are happening. If we did a real space-filling pi orbital, p orbital around each one of these, it would be like that. So there would definitely be some overlap. It's just, this way doesn't show it. Okay. So this is what the hybridization now looks like, right? The p orbitals and the s orbitals together give you something in between, and you have 3 degenerate orbits. Plus this one unused p that's still at the same energy level as before. Okay, so this is an artist's rendition. And of course, those electron density diagrams here are squeezed so that you can see more of the action. If we made them real shaped, then this one would probably hide that one behind it, and this one would hide that one behind it. It would be so big. But if we draw it this way, then we can sort of visualize better where everything is. So these 3 are responsible for the trigonal planar of those 3 right there. And then the double bond that forms is attributed to overlap of this one with its neighbor. Okay, so this is what the space filling model would look like for those orbitals. They would be pointing in. They would be pointing to the apex, each apex of an isosceles triangle. Okay, how about, oh, we're still talking about sp2. All right. Oh, okay, so here you've got the hydrogens overlapping their s orbitals with the sp2 hybridized orbital. Right? And then you get the sp2s here giving you the sigma bond between the carbons. And then, of course, you get the overlap. Don't forget top and bottom on the unused p orbital. Okay. So let's see if we can expand. Let's see. I'm going to erase that one there. CO2. So let's do the CO2 dot structure. Right? Carbon has 6 valence electrons. Right? Oxygen has, 4. Duh. Oxygen has 6, so it has 12 total, which means 16 electrons. Now we can put the carbon in the middle. 1, 2, oxygen, oxygen. So that's 4 from that one would be 12. So we have like that, and like that. So that's 12 electrons. We're done. Now we just need to make octets. So oxygens have octets, but carbon doesn't. So we just take one of those here and say one pair there and one pair there. So that gives us there we go. So that's our carbon dioxide molecule with the localized electron model. The VSEPR tells us that molecule is linear because you only have 2 here. Okay. So there it's linear and the bond angles are 180 degrees. Okay, so now what do we do with that? Well, with this carbon, how many equivalent orbitals do you need? Well, you only need 1 for this side and 1 for that side. You only need 2. You need 2 orbitals. So we only need to hybridize 1s and 1p. And an sp hybrid always gives you a linear electronic configuration. In this case, it's also molecular configuration. Well, how many P's did we not use? Well, let's say we used a P sub X for that one. So that means we've got P sub Y and P sub Z left over, unused. Okay, so if we have one going this way like that, we have another one going like this and like that, then all we need is some way to overlap with oxygen. But what does oxygen have going for it? Right? Oxygen has 1, 2, 3, right? So it's going to be, it needs 3. So oxygen's going to have Sp2 hybridization. Correct? That means it has 1 p orbital left over for each one. Okay? So these two, like that, and like that, and then these two, like that, and like that, give you your pi bond here and pi bond there. So this one's sp hybridized, oxygen is sp2 hybridized. And that gives you 3 equivalent orbitals, but 2 of them are filled with lone pairs. And then you have the unused P's to overlap with the carbon P orbitals. Okay, so now we're just talking about carbon. This is the carbon diagram. So you've got these 2 equivalent degenerate orbitals, and then you have 2 unused p orbitals. And those are the ones that are responsible for pi orbital on that side and the pi orbital on that side. Now I'm not sure if this, let me look at my hard copy before I steal my own thunder. Yeah, we're going to talk about it in just a second, about the oxygens. So I have kind of jumped the gun a little bit. So this is what the carbon would look like. It only has 2 equivalent orbitals. It only needs 2. Sp hybridized. So those are your sp hybridized orbitals there. And they interact with oxygen. And notice that this is a trigonal planar here. This is a trigonal planar here. Only notice it's turned on its side, which is perfectly all right. And then each oxygen has this gold colored unused P, unused P, unused P, whereas carbon has 2 unused P's. There, and there. You know, I just noticed the artistry can only go so far in trying to show you reality. Notice that this is considered 1 orbital right there. This is considered another p orbital like that. But this is considered 2 orbitals right here, 1 on either side. Okay, so you have to sort of stretch your imagination and bend the rules a little bit, because you would expect it to have 2 lobes. And if we look over here, in fact, one points that direction with a tiny lobe on that side, and the other one points this direction with a tiny lobe on that side. So we could reasonably assume that the tiny lobe for this one is over here, kind of underneath, and the tiny lobe for that one is kind of over here underneath. So that's how I rationalize it anyway. Okay. So here we've got, this just shows you the hybridized orbitals. Right? For carbon, it's sp hybridized orbitals. For oxygen, it's sp2 hybridized. And these 2 on either end, there and over here, are occupied by lone pair electrons. Okay, now how about dinitrogen? Okay, 2 nitrogens. There. So we have 2 times 5 is 10. 10 electrons. So we have here and here. That's 2. It means we have 8 left over. So we have 1, 2, 3, 4, 5, 6, 7, 8. 2, 4, 6, 8, 10. 10 electrons. Now we need to make, is that right? Nitrogen. 1, 2, 3, 4, 5. 5, 10. Yeah, that's right. 2, there's 8. 2, 4, 6, 8. Okay. So, we've got 1, 2, 3 groups around that nitrogen. So we would expect sp2 hybridization, but I don't think that's right. Because what we would do, oh, I haven't finished. That one goes there, and this one goes there. So that means 2, 4, 6, 8. 2, 4, 6, 8. Okay. Now we've got this one right here. All right. Now we have 2 groups around each nitrogen, which is what? Linear. So it's sp hybridized. Okay, sp hybridization gives us room for a bond. One single bond between the nitrogens would be sp. And that means you have 2 unused p orbitals. So you have a p here, a p there, and a p back here, and a p back here. And those overlap, and these overlap to give you the other pi bonds. So you have 1 sigma and 2 pi bonds for nitrogen with sp hybridization. There we go. It's artist rendition. So there's your sp hybridization, and you get the overlap between the 2 nitrogens here. And yes. And the lone pair that's left over is in the other sp. One of the sps is used for bonding, and the other sp is for the lone pair. But you do have the other 2 pairs that are occupying the p orbitals, and they overlap to give you the 2 pi bonds. Okay. So as if that wasn't enough, let's make it more complicated. PCl5. Okay. Phosphorus has 5 electrons, and this one is 7 times 5. So that should be 40 electrons. Okay, with 40 electrons, and phosphorus is in the middle. So we have 5 of them. 1, 2, 3, 4, 5. Chlorine. So that's 2, 4, 6, 8, 10. That means we have 30 left over. And if we can put 6 around each one and make an octet. 6 times 5 is 30. So that would be all of them used up. Okay, there's our Lewis dot structure. Now, what's the, well, there are no lone pairs around phosphorus, so the electronic is going to be the molecular structure. So when you have 5 of them, what does the VSEPR say? Trigonal bipyramid. So you're going to have a triangle here with chlorine, chlorine, chlorine. Then you're going to have a chlorine up here and a chlorine down here with phosphorus in the middle, like that. Yeah. Trigonal bipyramid. Okay. So phosphorus can't handle that with its existing atomic orbitals, right? Because if it relies on s orbital and a p orbital, at the minimum, they would not be symmetrical. But this is a symmetrical molecule. We need 5 equivalent orbitals. So where do you get them? Well, look where phosphorus is located. Phosphorus is in the 3rd period, right? So if n equals 3, what does L equal? 0, 1, and 2. That's S, P, D. Now we have access to d orbitals. So we can hybridize 1s, 3 p's, and 1 d. So now we're going to do this molecule with 5 equivalent orbitals that are constructed from an s, 3 p's, and a d. Now, don't ask me why they put the d first. You would expect sp3d, but no, the way it's written in every textbook I've ever seen is dsp3. And this, since it's 5 equivalent orbitals, is always a trigonal bipyramid. Okay? And let's see. Trigonal bipyramid. Now, what kind of bond angles do you have? Right. Well, let's see. You have one, if you start here, the bond angle between that one and this one is 180. The bond angle between this one and that one is right angle, 90 degrees. The bond angle between this one and this one is on a trigonal, so it's 120 degrees. So you have those 3 possibilities. I'm not sure if now I left out the 180. But you do have a 180-degree bond angle there. And it's DSP3 hybridization. That's generally what it would look like. We haven't talked about chlorine yet, you know. Is chlorine hybridized too? Well, let's see. Chlorine only has to form a single bond, correct? Right. If it only has a single bond, and it has, let's see, chlorine has 3p. One of its 3p orbitals can handle that. And it looks to me like that's what's happening here. So chlorine is not hybridized, like hydrogen for methane was not hybridized. So chlorine doesn't have to hybridize. I suppose it could. And actually, the way they've got it drawn, it looks like it is hybridized. It looks like it is sp3 hybridized. Okay. So what do we got next? Oops, I erased that one. Let's fix it. DSP3. Okay. How about Xenon Tetrafluoride? Okay. This one has 8. This one has 4 times 7, which is 28 and 8 is, oh, strain my brain, 36. Okay, so we got xenon in the middle, and we got 1, 2, 3, 4 fluorines. 2, 4, 6, 8. So 8 from that is 28, right? 28 electrons. 1, 2, 3, 4, 5, 6. That's the most you can put around fluorine. So 6 times 4 . 6 times 4 is 24. So that leaves you 4 electrons. So we have to put those around the central atom. Okay. So what kind of electronic structure do we have? We got 1, 2, 3, 4, 5, 6. 6 groups around the central atom means octahedral. And these are all electronic structure. Okay. So what would yield that? You need 6 equivalent or degenerate orbitals. So what do? We'll just add another D, right? Because xenon definitely has access to d orbitals. I mean, it's period 5. D2 Sp3. Okay. So where are those lone pairs going to go? Well, if this is an octahedron, the best place for them is as far away from each other as possible. So they go at the top and the bottom of the octahedron. And the fluorines go on the square in the middle. It's like an Egyptian pyramid sitting on a pool of mercury. You can see its reflection. You see an upper and a lower half with a square base. So you need 2, 3, 6. 6 positions. 2 of them have lone pairs in them. What about the bond angles? Well, each one of these bond angles is 90 degrees, correct? And this one to that one is 90 degrees. But this one to this one is 180. So let me see, did I leave that one out too? I did put it in this time, 180 degrees. Okay. So that's how we use hybridization to fit with the VSEPR model. It gives us a structure, and we say, all right, what do you need? Well, you need 6. Here you need 5. Here you need 4. Here you need 3. There you need 2. Hybridized orbitals. Okay. So that's what it would look like. You've got these equivalent hybridized orbitals, and the 2 on the top and the bottom, those 2 have lone pairs in them. The fluorines are probably hybridized also, just like the chlorines before. You would hybridize the fluorines with Sp3s. All right. Let me see how we're doing on time. Oh, we've got lots of time. Check my hard copy. And we're going to go to concept check. HCN. Right? It doesn't say that's an aqueous solution, so what would we call it? Hydrogen cyanide. Right? If it were an aqueous solution, it'd be hydrocyanic acid. So which hybrid orbitals are used here? Well, we have to see. We got a 1 here, 4 there, and 5 there, so that's 10 electrons. We got a carbon, nitrogen, hydrogen, 2, 4. So that means 6 electrons left. So where are we going to put them? Well, we start from the outside and work our way in. There. There. Hydrogen can't take anymore, so we put them all on nitrogen. Now we're going to form octets. So we take these two over here and these two over here, and that gives us 2, 4, 6, 8, 2, 4, 6, 8, 2. Okay, we're good. So now we have those two used up, and we got this pair over here. So what's the shape around this one? It's linear, right? Linear. So we need sp hybridization here. How about this one? 1, 2. That's sp hybridization also. And hydrogen doesn't count because it only has an s orbital. Okay. So which ones are sigma and which ones are pi? Well, we got sigma in the middle, and we got pi up here, and we got pi down here, and this one is a sigma, right? Anything that's on axis is a sigma. So both of them are sp hybridized, like that. Okay, that answers all the questions, I think. Yep. Okay. We're going to have lots of time to spare. We can take all the time we want on these, because I'm gonna break between the valence bond theory and the molecular orbital theory. We're going to break right there and talk about the molecular orbital theory on Monday. So it'd probably be good for you to read that part of the chapter anyway. All right. So we want to determine the bond angle and expected hybridization of the central atom of each of the following molecules. So we're only going to focus on the atom in the middle. We did this one already. NH3. That one is N, like that, like that, like that, like that, right? And it's Sp3 hybridized, right? Bond angles are going to be something less than 109.5 because it's tetrahedral. Okay, let's scroll across the top. SO2. Right? So we have sulfur, which is in the oxygens group. It has 6. So 3 times 6 is 18. We got 18 electrons. So we need sulfur, and we need 2 oxygens. Right? So that's 2, 4, which is 14. And then we have this one, this one, this one, this one, this one. There, 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 there. So that's 12 more, which means we have 2 electrons left over. Okay? So around the central atom, we have trigonal planar. Trigonal planar means sp2 hybridization. And the bonds are going to be 120 degrees. Let's see. There you go. And there you go. How about Krypton Difluoride? All right. Well, I can move over here when I run out of room, so that's okay. Krypton Difluoride. Krypton is a noble gas, so it has 8 electrons. Fluorine has 7 as a halogen, so it's 14, and 8 is 22, right? Yeah, 22. So we have krypton in the middle, these fluorines. So that's 4 that's 18. So we have, how many we use here? There, 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 there. So that's 2 times 6 is 12, which means we have 6 electrons left over. So where are they going to go? There, 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 there. Okay, so around krypton, excuse me, not potassium, krypton. 1, 2, 3, 4, 5. 5 means DSP3. Okay, now how about the bond angles? Well, we only have fluorine and fluorine. Where are they going to go? Well, usually when you have 3 lone pairs in a trigonal bipyramid, the 3 lone pairs go in the triangle in the middle, and the fluorines go out. So it's going to be a linear molecule with a 180 degree. Why does it say 90? Oh, all right. I have a difference of opinion here with the authors. What they're saying is this trigonal bipyramid with krypton in the middle, instead of putting fluorines out here and lone pairs there, like that, they're going to put, I think they're going to put both of the fluorines here and put the lone pairs up there and down here. Well, that doesn't make any sense. 120 degrees, yeah, you could do that. But there are only 2 fluorines, right? So that's a mistake. If you put a fluorine up here, then you could have 90-degree angle, okay? But you can't have a 120-degree angle. You could have a 120 here without the 90, or a 90-degree here without the 120, but you can't have them both. Unless they're talking about resonance, and that would be new to me. I don't think that would work. Let's see. Went too far. Back up. I need to make myself a note here. Check on this one right here. Krypton Difluoride. Now the hybridization is correct. DSP3. But I'm not so sure about those bond angles. I would have expected the bond angle to be 180 degrees. But even if you put the lone pairs up here and put the fluorines on the triangle, you still only get 120-degree angle. Okay, let's move on. I'll finish over here on the side. Let's see, move that over just a hair. What's next? Carbon dioxide. All right, we did carbon dioxide already. Right. That's you need 2. Right. For linear, you need 2, so it's Sp hybridized here. And the bond angle is 180 degrees. Okay, that one's fairly straightforward. ICl5. Okay, they're all halogens. So you have 6 times 8 is 48 electrons. So you have I in the middle, and you have 1, 2, 3, 4, 5 chlorines. Right, so 2, 4, 6, 8, 10, 38. And we have the potential for putting 6 more around each one of the chlorines. So 6 times 5 is 30, correct? So that means you have 30, no, you have 8 electrons left over. Let me see if I did something right. 6 times 8. 6 times 8 is 48. That's right. 2, 4, 6, 8, 10 means 38. And then 1, 2, 3, 6 times 5 is 30. So that's 8 electrons. So where are the 8 electrons going? Well, they got to go on the iodine, don't they? Yeah, ICl5. So 2, 4, 6, 8. So that's 1, 2, 3, 4, 5, 6, 7, 8. That doesn't make any sense. What does it say? D2sp3. D2sp3 means that you've got an octahedral group. That means that you can only have, let's see, 5 times 6 is 30. 2, 4, 6, 8, 10, 40. I don't know about you, but that doesn't work for me. Oh, I can't even multiply. ICl5, 6 times 7, not 8. All right, let's try this again. And nobody stopped me. 6 times 7 is 35. So 10 is 25. 2, 4, 6, 8, 10. And then 6 here. 1, 2, 3, 4, 5. No, 5 times 6 is 30. Oh, now something else is wrong. 35. 2, 4, 6, 8, 10 is 25. And then you have 2, 4, 6 times 5 is 30. So that can't be. All right, let's start all over again. Start from scratch. ICl5, correct? ICl5. Okay, there's 7 there, and there's 5 times 7 here. So that's 35. Oh, 5 times 7 is 35, yeah. 35 plus 7 is 42 electrons. All right, now we're getting somewhere. Chlorine, 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 chlorine. 2, 4, 6, 8, 10. 32 left over. Right? So if I put 6 around each one of these times 5 is 30. Now we're talking 2 electrons left. 1, 2, 3, 4, 5, 6. Octahedron. D2sp3. Okay. So you're going to have this lone pair is going to be at the apex. So you have on the square, you have 90 degrees, 180 degrees. Well, you only have 180 degrees if you do it like this. One, two, three, four, like that. To make your octahedron. Then you got 90 degrees here, you got 90 degrees there, and you got 180 degrees there. If you put the lone pair on the square, if you put the lone pair up here, then you've only got 90 degrees. Okay. So what's next? We ought to be coming down the home stretch for the localized electron model. So we'll probably finish a little early. So when we use the localized electron model, this is just rehash. Specify Specify, after you do all the drawing and the structure, then specify the hybrid orbitals that you need to accommodate the electrons, either in bonding or in lone pairs. And you only have to consider the sigma bonds to make the VSEPR model work. Then if you do have some double bonds or triple bonds in there, then you use the unused p orbitals to make those overlaps. Okay, well this is obvious. Problems with the localized electron model. We assume that the electrons are localized. And we've already introduced one solution to that problem, the resonance, where you have equivalent, two or more equivalent Lewis dot structures. And you have to keep them all. Then you say they resonate among each other. I'm not so sure that it doesn't deal with molecules with unpaired electrons. It does. It puts them someplace, right? Sometimes they go into hybrid orbitals. But that doesn't always effectively describe what those electrons are doing. Example. For instance, with ammonia, you have one lone pair in a hybridized orbital. But if the structure of the molecule is correct, then even with the hybridized orbital, you should have tetrahedral structure, and bond angles should be 109.5 degrees, but they're not. They're less than that. So that being said, then we could possibly stretch to say they don't effectively deal with those molecules. Where are those lone pair electrons? It doesn't, no, that's true. It doesn't provide direct information about bond energies. It just says that the bond energies of the hybridized orbitals, the degenerate orbitals, are somewhere in between. But it doesn't say how much. It doesn't say what their values are. Okay, so here's where we're going to pause. The next slides get into the molecular orbital model. So I figured this was a good place to break. We don't want to go any further than this. And I've got some videos that I want to use, and let's see. I wonder if I'm going to have time to do them. 1, 2, 3, 4, 5. That's 30. 32 slides left. And we've already done 42. We may have enough time then. Because the videos that I picked, they were so good. I think there are 3 of them. I just couldn't bring myself to throw them away. So there's a lot of information in those videos that is rehashed. It's brought up to the surface again to give you a reference point. So if you sort of lose your way between now and next Monday, these videos should bring you back on track. Okay, any questions or comments?